What we're going to talk about now is the aspects of repair in terms of what is sulfur doing in our body to help with repair? What is sulfur doing in our body as a component of the structure of our body's tissues? So we're going to look at structure and repair in terms of sulfur. If we break down the composition of the human body, like this infogram is showing us, and we look at sulfur over here, sulfur is 0.2% of the elemental composition of the body. Now that's double the amount of magnesium. Magnesium is down here. It's 0.1% of the elemental composition of the body. Sulfur is the fourth most common mineral. So if we start over on the left-hand side here, we run through the more plentiful components of our body, and then we get into the minerals. So first we have calcium, then we have phosphorus, then we have potassium, and then we have sulfur. Sulfur is the fourth most common mineral that we find in our bodies, and there's twice as much sulfur in our bodies as magnesium. What is this sulfur doing? Well, the chemical properties of sulfur provide the aspects of strength and flexibility. So we need them in tissues that are going to be strong, but at the same time they're going to be flexible. So if you think about things in our bodies that have those aspects, you can think about hair and nails and tendon and connective tissue. They all need to have some give. They all need to have some little bit of flexibility, depending on what tissue it is, and strength as well. So both. If you compare that to, say, bone has very little sulfur in it because really what it needs is strength. It doesn't need to be flexible. We don't need flexible bones. We've got flexible tendons and flexible cartilage around the bones. We need the bones to be strong so they don't have a lot of sulfur in them. But these other tissue structures, like hair and nails, they have a lot of sulfur in them to provide that strength and flexibility. And the digestive tract is a really important part of this too, because it relies on sulfur for its elastic nature. So we can have these waves of peristaltic movement, moving things through the system. We can have stretch and we can have recoil. We can have permeability, so all really important in the gastrointestinal system. A tissue that has a low sulfur content, like this ball of elastic bands over here, is meant to represent that low sulfur content, which is providing the flexibility aspect of sulfur. And tissue that has a high sulfur content, like this bird beak here, that's showing the strength of the sulfur in tissue. So that, believe it or not, that bird beak does have a little bit of flexibility as well. Not much, but a little bit. So it's got both strength and flexibility. There's more sulfur in a bird beak than there is in, say, the digestive system. That requires more of a recoil elasticity effect. Now we're going to get into the protein structure. So let's just make this really simple. There's three levels of structure of protein. Our body is made of protein, not just the muscles, but there's protein in all of the connective tissues of our body. So skin, nails, hair, tendons, ligaments, obviously muscle. So if you look at that protein structure, there's a primary, a secondary, and a tertiary or third degree structure. The primary or first degree structure is just the linear sequence of amino acids. We have a limited number of amino acids, 20, and those build, by putting them in different combinations, those build different proteins. That's all you have to do is just mix them up in that linear structure to make a different type of protein, which is a combination of this strand of different amino acids linked together. Now, a strand is fine, but that doesn't really help us much for function. So then we start getting into more of the secondary structure of protein. And what happens here is you've got interactions between the different, we call them R groups, on the sides of each of these amino acids, and they interact with each other, pulling them together to create things like the alpha helix, which is this spring-like structure here, or the beta-pleated sheet. Both of those two are secondary protein structures. Tertiary protein structure is the three-dimensional structure of a protein, and that's formed again by these R group or side group interactions of the amino acids with each other, and their stronger interactions. They consist of three different types of chemical interactions: ionic, covalent, and hydrogen bonding. So that's the third level of structure, the three-dimensional structure of proteins. Now, if we look at the strength of these different interactions that create the three-dimensional structure of proteins, which is literally the three-dimensional structure of you, of your presentation, and we go from weaker to stronger. First of all, you have very weak forces like van der Waals force. Now, these are just clouds of electrons that form and disperse. So they're very weak in terms of what they're able to do. The next level of strength is hydrogen bonds. This is an electronegative pull from one atom to another. Hydrogen bonds are called that because they're found pulling electronegative attraction between water molecules. Water is H2O. So if you look at one of these little groupings of three, you can see two H's and one O, that's water, and the oxygen from one water molecule is literally pulling, because it's stronger, so it's pulling that electronegative force from the hydrogen, forming a weak bond within the structure of water. Incidentally, that's one of the reasons why water is one of the only elements that the solid form is less dense than the liquid form, right? Ice floats on top of liquid water. Ice is less dense. That's the solid form, and the reason for it is because there's these spaces that get created by the hydrogen bonds that make the solid form of water less dense than the liquid form. The next level of strength in the chemical bonding are the ionic bonds. Ionic bonds are literally one atom will take the electron out of the outer shell of the other atom. So an example of that is salt, or sodium chloride, NaCl, sodium chloride. Now, in a pure chemical solution, in a pure chemical situation, you will have a very, very strong bond when you have an ionic bond. But in a biochemical solution or biochemical situation, like a human body, we're aqueous. Everything is in water in us. So what we have is a weaker bond when it comes to the ionic bond, because that bond can dissolve in water. Just think about when you take salt and you put it into water, what happens? It dissolves into its two components, sodium and chloride. So that leaves ionic bonds being the third most common or third strongest bond in a biochemical solution or a human body, an animal body. That leaves the strongest bond in a biochemical system, the covalent bond. The covalent bond is literally a sharing of electrons, so it kind of goes back and forth between one atom and another to hold that together. And the majority of these covalent bonds that are found in our proteins are the sulfur bonds. That's how we circled back to sulfur in all of this. These sulfur bonds are called disulfide bonds because it's literally two sulfurs linked together, disulfide, and they're the covalent linkages on the side chains of proteins that are holding that protein in its three-dimensional structure. We know that these are stronger than any other type of bond that contribute to the tertiary or three-dimensional structure of proteins. So they're literally acting like safety pins holding the polypeptide or protein firmly in its three-dimensional structure. So if you look at it here, there's an example. The sulfur bonds, the disulfide bonds, or two sulfurs bonded together are safety pins, right? They're holding the structure together. The more safety pins you have, the more principles of strength you have in a tissue, like your fingernails. The less sulfur bonds you have, the more principles of elasticity you have in a system like your digestive system. And to look at this from another aspect, we know that we've got now again elastic recoil, we've got motility, so those are the systems that have less sulfur bonding, and then we have strength, the systems that have more sulfur in them. And the proteins that are rich in disulfide or sulfur bonds have those mechanical properties like tensile strength, viscosity, and hardness, and those correlate with the degree of sulfur bonding. So if you look at a system that has few sulfur bonds, like gluten has sulfur bonds that impart the cohesive and elastic character of the dough made from wheat flour. So have you ever seen flour being made, or pizza being stretched, or any kind of bread being made? What you find is that there's that elasticity of it, right? It can stretch and it can recoil. That's coming from the gluten protein. And within the gluten protein, it's coming from those stretchy safety pin sulfur bonds, all the way up to the hard, tough nature of a tortoise shell, which results from the sulfur bonding with the alpha keratin. So relatively speaking, you've got way more sulfur in a tortoise shell than you have in the gluten when you're making bread, and that sulfur is interacting with the alpha keratin to form this very, very hard structure. It still has a little bit of flexibility, but it's very hard and tough. So how do you make one of these sulfur bonds? Well, this is just like a little brief overview of the chemistry. So you've got two cysteine molecules, one here and one here. And that is the amino acid. That's the building block of proteins. Now this cysteine will interact with the other cysteine right here, where you've got it's called a sulfhydryl group, a sulfur and a hydrogen together. Now what the chemical reaction is a reduction reaction where you remove each of these hydrogens. Here they go off here, two hydrogens and two electrons, they have to go together. And let's follow this arrow along here. You end up with the no hydrogens, so the sulfur is bound to the sulfur, and that creates a new amino acid that we call cysteine. So they're not that much different in terms of what they're called. You just drop the E from when it was a smaller, two-pronged situation. Now that it's one whole amino acid, it's a new amino acid, and it's called cysteine. So that can be a little bit confusing because you just made a new amino acid out of two amino acids. But what's holding them together is a sulfur bond. That's the take-home message right there. Now let's apply this to the body. So our body contains something called glycosaminoglycans. You might have heard of one of those. Hyaluronic acid, kind of sweeping the nation in terms of, using it in skin products to help support collagen. Well, that's a little bit of a problem because hyaluronic acid itself is such a huge molecule. There's no way it's going to get through your skin. But, things get marketed, so that's where we're at with that. But the rest of the glycosaminoglycans, those are basically disaccharides. That means it's a sugar molecule that are linked to a polypeptide core. Polypeptide is a protein, and what they do is they connect collagen fibers together. Now, inside that polypeptide core, what we've been talking about, proteins, is sulfur-based proteins. and that's the safety pins that are holding your collagen together. So those are important. Sulfur is important for collagen formation. These glycosaminoglycans are called heparin sulfate, chondroitin sulfate, keratin sulfate, dermatin sulfate. You might recognize some of those from the supplements that you take. Chondroitin sulfate, for example, you might be taking that for joint support. It's the same principle. That glycosaminoglycan is helping to create connective tissue, which is what joint tissue is. So if we think about collagen, we know that collagen forms and repairs our connective tissue throughout our body. So then we can think about leaky gut syndrome. It's connective tissue. It's leaky. We need collagen to reform and protect it. And we lose collagen by the amount of 1% every year after the age of 25. Collagen accounts for 30% of your body's total protein. 30%. That's significant. Now, when you have a collagen powder, does it contain the sulfur you need to hold the collagen together? No, it doesn't, because when the collagen is hydrolyzed, that means chopped up into those small pieces where it can actually get into your body. When it's hydrolyzed, the sulfur ions are released, so you don't have any sulfur in there. So in order to reform that back on the other side, you take the powder, you put it in your mouth, and then you drink it. It's going to go in there, and you've got the collagen part, but you don't have the sulfur part to reform it. So that's important to think about in terms of using collagen powders and being able to use them for repair efficiently. So let's translate that into some of the body structures. If we're talking about the digestive system, again, you're going to have sulfur bonds in the digestive system to give you the principles of motility, to give you the principles of stretch, of recoil, elasticity, as well as permeability. So all those things are really important. Now, I hear a lot of people talking about motility. There's this theory that once someone gets SIBO, or small intestinal bacterial overgrowth, they lose their motility. Well, that's contrary to what I find with this treatment. When you replace sulfur in the system, the motility also regenerates in the digestive system. So I really don't feel the need to use any additional motility work with my patients. I just use the GI Gen 1 powder. We get a reestablishment of motility or peristalsis, or muscle movement within the system. And if you look at this, it's kind of interesting. If we look at the anatomy, at least, of the digestive system, here we've got the stomach. Well, in this diagram, it's inverse. The stomach should actually be flipped on the other side. So mirror image of that. Somebody didn't do a good job program here. It wasn't me. But if you look at the differences between the structure of the tissue, you've got the esophagus is a tube, you've got the stomach, which is an enlargement of this tube, and then it gets smaller again and goes into the small intestine, which is all coiled up in here in the middle of the body. The small intestine then dumps into the large intestine, which goes up, across, down, and out. Now, each of these different shapes, as you move through this 30-foot long structure, are all responsible for different things. The esophagus basically is transport down into the stomach. The stomach is the initial part of digestion. You're going to release hydrochloric acid in there to kill any bacteria that come in with your food, and to start churning the food up and mixing it to get it ready to be digested. And then from the stomach, you get it dumped into the small intestine. Now, this 25-foot piece of small intestine is all about breaking down your food into the size that can go into your body from the small intestine, and absorption into your system. So this is only 1 cell thick, because that's where we transport the nutrients that are going through us into the bloodstream, so they can be used by the body. Now, by the time the food gets to the end of this system right here, and it goes into the large intestine, all of the nutrients are absorbed, and this now becomes compacted as we take out water. Absorbed water goes out, and this moves through. That's motility, peristalsis moves through and gets more and more compacted as we go through the system. You end up with the waste in the rectum, and then you get the signal that it's time to move your bowels once it's in the rectum in a perfectly working system. So again, it's the disulfide bonds that are important chemical properties for the cross links that control elasticity and motility in the digestive system. Let's look at hair. The strength of our hair is primarily from sulfur bonds. So when you're perming your hair or you're straightening your hair, what you're really doing is you're putting your hair into the shape that you want, and then you're applying a chemical that breaks the sulfur bonds, and then you're applying another chemical that reforms the sulfur bonds in the new patterns, so that if you say you're perming your hair, you put it around the curlers, and then you break the sulfur bonds, and then you reform them. And when you reform them, you're reforming them in the shape that you want. So you take out the curlers and you've got that permanent shape. And if you've ever smelled a perm, you're going to smell sulfur, because you're breaking and reforming those bonds. You're actually releasing some hydrogen sulfide gas. And this sulfur bond is so strong that 9,000-year-old hair has been recovered from archaeological sites. That's how strong the sulfur bonds are to keep hair intact for that long. If we look at our nails, the sulfur bonds in the cysteine, we looked before at cysteine, which is that, the chemical formation of those sulfur bonds, they contribute to nail hardness. So it's the sulfur bonds interacting again with the alpha keratin that give us the tensile strength in the nails. And contrary to what is popular belief, calcium only makes up about 2%, 0.2%, very small amount of the nail plate. It's really the sulfur that's the major building block for strength in the hair and in the nails. And you'll find too, as you go through this protocol, that the nails and the hair do respond in a positive way as well. If you look at feathers, the strength of feathers is due to the sulfur bond. And in fact, if you ever smelled a rotten egg, you're going to smell hydrogen sulfide gas, because eggs are full of sulfur, because they need to be to provide sulfur as a nutrient for the developing bird species to form those flexible yet strong feathers, talons, and beaks. So we're going to move on from here, and we're going to talk about the other properties of sulfur, which are antibacterial and antifungal properties.